Welcome. This presentation is about cross-layer design for quality of service support in ad hoc networks. This presentation is prepared by Hisham Al-Gaziri, Mirna Yaoud, and Hazem Amin. First of all, a brief introduction about the main ideas or the main vocab we're using in this presentation. What are wireless ad hoc networks and mobile ad hoc networks? Wireless ad hoc networks, or WANET, is a decentralized type of wireless network where there is no existing network infrastructure such as routers or access points. Instead, each node has equal participation in network routing by forwarding data to other nodes. As for mobile ad hoc networks, they are considered to be collections of nodes that form a multi-hop wireless network. They are being used in a variety of applications from emergency rescue to sensor networks. So, what is quality of service? QoS refers to the ability of a network to handle traffic such that it meets the needs of certain applications. This would require the implementation of traffic handling mechanisms in the network while having the ability to control such mechanisms and to identify network traffic associated with these mechanisms. Okay, so there are challenges in ad hoc networks that make quality of service hard to implement. But first, we need to see the requirements of different applications for quality of service. How could they be expressed as parameters? These could be summarized as bandwidth, latency, jitter, and loss. The bandwidth is the rate at which an application's traffic must be carried by the network. Latency is the delay that an application can tolerate in delivering a packet of data. Jitter is the variation in latency, and loss is the percentage of lost data. So back to the first question, what are the challenges in ad hoc networks that make quality of service hard to implement? These include wireless links are very unpredictable, node mobility, no centralized control, route maintenance, and data loss. Okay, so we're using in this presentation cross-layer design in order to enhance the quality of service in ad hoc networks. So the main idea of cross-layer design is to maintain the functionalities associated to the original layers, but at the same time allow coordination, interaction, and joint optimization of protocols crossing different layers. Admission control on demand routing was proposed to efficiently provide end-to-end support for quality of service by introducing simple functions which represent quality of service metrics and ensure implicit resource reservation. The aim of admission control is to determine whether the available resources can meet the requirements of a new flow, maintaining bandwidth and delay levels for existing flows. For bandwidth and delay estimation, to offer bandwidth's guaranteed quality of service, the residual end-to-end bandwidth must be known. This is a trivial task in wired networks since the medium is a dedicated point-to-point link with fixed capability. However, in wireless networks, the radio channel of every node is shared with all its neighbors. Due to the shared medium, a node can successfully use the channel only when all its neighbors do not transmit and receive packets simultaneously. We use a simple and efficient method to estimate residual bandwidth by listening to the channel of the IEEE 802.11 MAC. This method is based on the ratio of free and busy time. Neighborhood maintenance. Neighborhood information is very important since it provides the mobility information, traffic, and local topology. This information is critical for traffic measurement and route failure detection and recovery. For the route discovery and route resource reservation, admission control on demand routing works with as a pure on-demand routing protocol. No routing table is saved and no exchange of periodic routing data is done. When a source node needs to create a route to another node with the limitation of specific quality of service requirements, it sends a route request packet which only includes the requested bandwidth, delay, and also the global cost function which will be accumulated at every participating node to establish this route. Once the destination node receives the route request packet, It responds by unicasting a route reply packet, which includes the source node's address and the end-to-end value of the global cost function, to the source node along the reverse route. About loop-free routing. The destination sequence number is maintained at each node for the IP address of the destination for which the route table entry is maintained. This sequence number is updated whenever a node receives new information about the sequence number from route request, route reply, or route error packets that may be received related to that destination. Using this technique, ACOR guarantees that along the discovered route no three intermediate nodes will be within the same neighborhood area of each other. This property reduces the control overhead by minimizing the transmission of unnecessary control packets. The cross-layer design with admission control on-demand routing. The proposed scheme is based on the interaction between the 802.11e MAC and the ACOR routing protocols. Therefore, ACOR's packets are differentiated at the MAC layer. The header of these packets is then changed according to the quality of service parameters. This allows the continuity of quality of service between different OSI layers. About scheduling. The layer that is responsible for both scheduling and allocating the wireless channel is the MAC layer, or the Media Access Control layer. The choice of both the scheduling algorithm and the process of allocating the wireless channel affects many things, example available bandwidth and packet delay. The available bandwidth and packet delay influence the choice at the routing layer for the selection of the link. The routing layer is the one responsible for choosing the wireless links in order to transmit packets to the assigned destination. This routing choice assigns the controversy level at the MAC layer, which will, as a result, affect the parameters at the physical layer. One type of a proposed scheduler is a priority-based scheduler at the MAC layer for multiple connections with various quality of service specifications. AMC, or Adaptive Modulation Encoding, is a technology which can automatically modify the modulation to compensate for changes in link conditions. A proposed idea is to define a priority function which will be assigned depending on how good or possibly strong these three parameters are. The three parameters are wireless channel quality, quality of service satisfaction, service priority across layers. Now, talking about the service differentiation frameworks. Wired networks, they have widely used models which are integrated services and differentiated services. Unfortunately, those are not suitable for mobile ad hoc networks due to mobile ad hoc network specific characteristics and features which mainly defines them. These include mobility of ad hoc networks, dynamic network topology, bandwidth constraint, and limited power of nodes. So in order to satisfy quality of service requirements generally, there is a need to have a complex framework or quality of service model which can provide basic architecture of quality of service provisioning. There should be the cooperation among routing, queuing, packet scheduling, admission control, signaling, and traffic engineering. Mostly used quality of service models designed for mobile ad hoc networks try to reach these performances or goals. These include the flexible quality of service model for MANETs, integrated mobile ad hoc quality of service framework, insignia model, design of an efficient quality of service architecture model, cross-layer interactions and service mapping quality of service model, and stateless wireless ad hoc network quality of service model. So to summarize and sum up all these previous long points, the nature of ad hoc networks as infrastructureless networks introduces new problems due to the network mobility, lack of center control, and the continuous route maintenance. This led to approaches to accommodate with these problems in order to implement quality of service using cross-layer design. ACOR protocol aims to find a feasible route according to application quality of service requirements, taking into account new ways of calculating bandwidth and delay estimates, route maintenance, and recovery. Scheduling algorithms in general are implemented to handle the order, in which connections are admitted in order to achieve higher quality of service. In order to satisfy quality of service requirements, there is a need to have a complex framework or quality of service model which can provide basic architecture of quality of service provisioning. There also should be cooperation among routing, queuing, packet scheduling, admission control, signaling, and traffic engineering. Thank you for listening to this lecture and hope you enjoyed.